Alrighty. Awesome. All right. Hello everybody. I appreciate the opportunity to present in front of you today. As mentioned, my name's Mark Knoll, and I'm the value-added product specialist for Innicon here in the GTA. Today, I'll be speaking briefly on our EcoPack brand of sustainable concrete. And before I start, I'd like to thank our development partners, Daniels Corporation, for providing me the opportunity to present these carbon reduction solutions for you today. So next to water, concrete is the most widely used building material product in the world. With global warming challenges worldwide and the growing demand for sustainable building, Innicon and our partners at Amrise have created a low carbon solution for concrete. Reduced carbon emissions and strong technical benefits is why our EcoPact brand is recognized globally. Right now, we currently offer EcoPact and EcoPact Prime in our GTA market, with EcoPact Max and EcoPact Zero coming in the near future. So, what is EcoPact concrete and what makes it low carbon? So, EcoPact is our global range of low carbon concrete solutions designed to reduce embodied carbon without compromising performance. It incorporates supplementary cementitious materials, otherwise known as SCMs, such as granulated blast furnace slag and fly ash, as well as innovative admixtures and optimized mix designs. By leveraging these technologies, our EcoPact brand can achieve up to 70% lower CO2 emissions. For those of you that don't know, slag is a byproduct of steel production. It's the stony waste matter that gets separated from metals during the smelting process. And fly ash is a powder byproduct of burning coal and power plants. So it's great to be able to use these byproducts in another manufacturing process instead of needing to store these materials at landfills or waste management sites. So as mentioned on the previous slide, in our current market here in the GTA, we offer EcoPact and EcoPact Prime. EcoPact is designed to have a 30 to 50% carbon reduction when compared to an OPC, original Portland cement-based mix. EcoPact Prime has a 50 to 70% reduction. And when we talk about a CO2 reduction, we're referring to the GWP, otherwise known as global warming potential, which is measured in kilograms of CO2 emitted in the production and delivery of 1 meter of concrete. So this includes everything from the CO2 emitted in the manufacturing of the raw materials and the transportation of all our products that go into our mixes. So how is the process of creating EcoPact different from a non-green concrete? So it's through using cement optimization, using byproducts such as slag and fly ash, using ready mix additives, so the usage of admixtures to help with the reduction of cement, circular economy practices, so the use of recycled aggregates, and then ensuring that we have material delivery optimization with our truck routes. So when concrete is returned from a job site, it's emptied at the plant, transferred over to a depot where it gets crushed, and then it gets taken back to our ready mix facilities where we can then reuse the crushed aggregate in some of our approved mixes. So this ensures that most of the concrete waste is being reused and recycled. This here is an important slide for engineers and architects, designers and builders in generals to understand set time versus GWP. So with EcoPact Standard, the mixes set and cure in the same fashion as standard concrete. When we get into the EcoPact Prime mixes, however, there are possible delays in set times, and the curing does get delayed for some of our mixes. So instead of a standard 28 days to reach full strength, with most EcoPact Prime mixes, it requires 56 days to fully cure. So there is a little bit of a give and take between the CO2 content targets and build time scheduling. So what are some of the benefits of sustainable concrete? We've poured thousands of meters of EcoPact over the last few years, and the feedback from job sites and finishers has been great. There's really no difference in the workability and the finishing when compared to OPC mixes, and you get the additional benefits of CO2 reduction, increased durability and longevity over time, greater waste reductions and energy efficiency, and of course, EcoPact concrete meets regulatory compliance and low carbon building standards and with LEED certification. For any of our EcoPack mixes, we're also happy to provide Type 3 EPDs, which are independently verified by a third party. They also report our product, facility, and supply chain specific data and have validity dates included on them. So it's a very detailed document reporting all relevant GWP information for our mixes. And last but not least, this slide here provides the information on what our quality team requires from our customers in order to design your EcoPack mixes. So we need to know our supplementary cementitious material limits, as well as the GWP presets. And we can take that in the form of maximum GWP per mix, or as a GWP reduction percentage compared to baseline CRMCA values. Aside from that, any standard structural concrete specifications also need to be included, and the mixes can be designed from there. So that's it for me. Thanks again for the opportunity to speak today. And with that, I'll pass it over to Megan from the Daniels Corporation.
Awesome. Thanks, Mark. Just gonna take a second to steal the screen share. I think we're live. Okay, cool. Yeah, thanks everyone. So as Anna mentioned, I'm Megan Wilson, Senior Manager of Sustainability here at Daniels, and I'll be co-presenting with my colleague Adam, who's a Vice President at Daniels as well. I'll be leading the presentation, but Adam will probably jump in with some colorful commentary whenever he sees fit. So just stay tuned for that. All right, so today we're presenting a presentation called Lower Carbon Concrete from Concept to Construction. So this is really a deep dive into a specific pilot project where we work closely with the Innoconn team to deploy the EcoPack low carbon concrete really at scale, and how this expanded into a little bit of a broader study internally in terms of waste, strengths used, various additives, and overall key takeaways from really just diving into the detailed as-built concrete on site compared to what we anticipated in the design. Lag there. Okay, so shameless plug as always. So please read our decarbonization roadmap. This is sort of our internal framework for how we plan to decarbonize the built environment in our new construction projects, namely outlining our approach to whole life carbon intensity. So how we're combining both the embodied carbon intensity, so that's all the materials, including concrete, as well as the cumulative operating emissions to create this metric of the whole life carbon, and how we're looking to reduce that over the next couple of generations of our projects in our pipeline. So where we're at today, so right now we're in the kind of first gen of our decarb roadmap, where when we take sort of our baseline projects, in terms of the average sort of end use in terms of the whole life carbon, you can see the operating end uses in orange tones and the upfront or embodied carbon contributions in blue tones. So what we've sort of done to date in terms of getting from a baseline to Gen 1 is sort of chopping off that top line, so tackling heating emissions by electrifying formerly natural gas into electric heating for a lot of different projects. But when we get to this Gen 1 sort of distribution, you can see things like concrete become an increasingly large portion of the pie, which is why we wanted to work closely with Innoconn and look for low carbon concrete substitutions. So we've got 4 buckets when it comes to concrete that we'll be looking at today. So really it's the use of EcoPact, both the standard and the prime product, as Mark outlined, the volumes that were used on site compared to the design, as well as the strengths, and evaluating additives as well. And all these 4 things really funnel into 2 key parameters, including cost and carbon. And so we like to try to marry cost and carbon together, especially when we talk about concrete, because there's a lot of value that can be driven from not just reducing concrete emissions in terms of choosing lower carbon substitutions, but if you just reduce your volumes and strengths altogether, you're also kind of saving cost and carbon to really have this value-driven solution. But first, we'll start with the EcoPack stuff. Okay, so the first thing to note is sort of the origin of this initiative. So we, of course, have a longstanding relationship with Innoconn, who's concrete supplier who distributes formerly Lafarge, but I believe they just rebranded to Amrise concrete products, including the EcoPact line. And so when they first started promoting the EcoPack line several years ago, we, of course, wanted to implement just right off the bat, we're like, yes, this sounds like us. Let's do it. But it's of course impossible to confirm. It was at that time, it was impossible to confirm whether the product could be sort of baked into the design as a reliable embodied carbon reduction measure, since we needed to get buy-in from the site implementation side. Because in reality, what actually gets poured on site is what sort of dictates the real carbon footprint, not just the theoretical design LCA. So of course, you could specify like, yes, let's do it. But if it's not actually going to happen, can you really claim those reductions? So that's sort of the homework we wanted to do before we could really commit to this. So what we did was pick a project that was about to start construction at that time, a couple of years ago, and just try to pour as much EcoPact as possible without impacting the schedule. And so we met with site and with the Innoconn team weekly and monthly to really get feedback on the live site conditions, evaluate different elements where it could or couldn't be poured, and just get a ton of extra data in terms of site conditions, workability, cure times through extra break testing to just, again, debunk this whole thing. So back to the plan, which is kind of lifted on the table on the left. So the plan was to use as much EcoPact as possible, except where EcoPact mixes weren't available. So that included piles, because those were concrete was supplied by a different contractor, as well as foundation walls, which were done with shotcrete. So that's like the spray-on concrete. So that wasn't available in an EcoPact mix at that time. And then everywhere else was supposed to be EcoPact standard. And then on top of that, where possible, we also wanted to layer in the EcoPact Prime specifically on elements that were off the critical path, such as elements of the foundation, as well as partial transfer slabs. And that would just ensure that the schedule wasn't impacted by those longer cure times, as Mark indicated. So the total anticipated EcoPack volume was deemed to be about 85% of the total project was feasible to be cured in EcoPact mixes, and we were able to achieve about 72%. And I'll get into kind of the reason where we didn't quite hit the 100% EcoPact in the feasible locations in just a minute. But overall, we were able to pour over 22,000 meters cubed of concrete in the EcoPact mix, which is super significant. And I believe it's still the largest deployment of the EcoPact product in Ontario to date, at least in multi-residential. I'm not sure if that changed. Okay, so again, as I mentioned, what kind of led to this what was the biggest contributor to us not meeting the full 85% target? And it was really a lot of the challenges related to cold weather conditions and just the perception and buy-in from the site team at this time as we went through the project. So WeatherMix is an additive that gets incorporated into the concrete when the temperatures drop below a certain threshold to help cure the concrete in cold conditions. So it's really staple in the Canadian construction industry and helps us pour concrete all the way through the winter, 12 months a year instead of just, let's say, 8. But it really adds another challenge when trying to reduce embodied carbon because you have sort of these competing interests between trying to cure faster, whereas inherently lower carbon concrete tends to go slower. So there's a bit of kind of competing interests in that respect. However, EcoPact standard is supposed to be like with typical concrete, and it is available in a weather mix option. And but you can see here sort of the seasonality in these curves between sort of the EcoPact pours shown in green compared to when weather mix is also being used. You see there's a little bit of a trade-off between the two in terms of just buy-in from site, really. So especially in the first winter, there was a huge pressure in terms of schedule in order to, we said, okay, we're going to do this pilot, but there's got to be no impact on schedule. And so just in terms of being able to deliver on that in the coldest months of the year, even though on paper, EcoPact is supposed to be like with like, it was still seen as a potential risk. And anything that was even a potential risk or perceived risk was pulled back in just like the most intense schedule months and especially in the coldest seasons. So this is why we saw sort of mixed results during the coldest weather, but we do have testing data that shows that there was no significant difference between the low carbon and the typical concrete with weather mix. But even just the perception again of that risk was enough to kind of start pulling back on some of the EcoPack deployment in those months. And that's something that we want to work on for our next projects of how do we get that sort of full buy-in going forward, that this is a product that works and we can rely on. So overall, it was positive, but just that was like one area where we just struggled in terms of getting 100% buy-in. So this is sort of a similar data, but just shown in a different way. So now this is stacked by, instead of by month, this is stacked by level. So this is kind of where we were able to deploy the EcoPact on a level by level basis and how much sort of the prime, which is in light green, prime, which is in dark green versus the standard EcoPact in light green, and the non-typical concrete is in yellow. So you can also see a little bit of seasonality here as well. But I'll start sort of below grade. So you can see in the lowest level here, we have actually a significant portion of the prime being used, and that represents those foundations, including the grade beams, caisson caps, footings, that we were able to pilot the prime product and we had really positive results on the performance of that product as well, especially in these non-critical path elements here. Below grade and some of these sort of P1, P2, you can also see that there's a significant amount of typical concrete as well. That represents the shotcrete being used, as well as in the early days of this pilot, there was a few non-air mixes that weren't available as we were going through it in the EcoPack. So that's sort of where that contribution comes from. But when we sort of started coming up above ground, especially in the ground floor, mezzanine, and level 2, that's when we hit that really cold weather and just winter conditions in that first year. So there was sort of a significant drop off in concrete usage, in the EcoPack usage at those times. But then we quickly came into the next spring and into the podium and the tower from levels, 3 to 16. That was sort of the good weather, good pouring months, and we were able to achieve extremely high levels of the EcoPack product there. You can see again, chronologically, when we get up to 17 and up, that's sort of the crunch time in terms of the schedule. It's a really tight sort of pouring schedule with the form workers and things like that. And it's getting into the second winter. Again, we lost a little bit of the buy-in with the site team, just with the schedule pressure and just some of the uncertainty around it, but we did see some sort of inconsistent usage of it there. So again, just working to get that buy-in through the winter season is going to be critical to increasing our overall deployment numbers. Okay, so now this chart here at the bottom shows sort of where the EcoPact was used now by element. So this shows, again, when you look at the biggest two, that's our slabs and beams and columns and walls. If we're able to get buy-in on the winter months, we would be able to pretty much bring these two columns almost up to 100%, and that would represent pretty much the shortfall in our EcoPack usage on this site. So it's really, again, getting buy-in on cold weather conditions, which is sort of an us problem, but we're working on it. Similarly for prime, if you notice here, we used a lot of it in the grade beams and footings, but we actually didn't end up using much of it at all in the transfer slabs, which was part of our original target. And that was due to just some site coordination, like when are elements being poured. It was just, things move really fast on site, obviously. So just getting that coordination and getting in at the right time to say, hey, you're about to pour a transfer. This is what we want to do. Try to order the prime product and just have that tighter coordination and more in live time, I think would be essential to being able to expand that in the future as well. What was interesting is that for the prime product, it performed really well, but the biggest risk we saw was not actually in the curing time, because you can control for that. You can just plan for, again, elements off the critical path. But the biggest challenge was actually in the workability. Since it comes in lower slump, so it's more viscous, call it. It's harder to work with. And so there is actually a higher risk that the site teams would then add water to the mix on site to increase sort of the workability. But that could have compromised the integrity of the entire pour. So that is something that just we noted has to be monitored really closely in terms of whenever you're using low carbon concrete mixes, is the actual sort of site conditions and who's handling it, and do they know that this mix isn't supposed to behave 100% like normal concrete, so that they know not to add water, things like that more on the site implementation side, or something that has to be considered. Okay, so then the overall carbon results. So this is a little bit different than Inacon's numbers, just in the way that it's quantified. So in terms of when we added the EcoPact initiative, So we actually already completed the design LCA prior to the implementation of this EcoPact initiative. So the design LCA does not actually include any benefit from the EcoPact product at all. But what we found actually when you look at the as-built and the concrete logs is that when you use the actual concrete strengths and volumes on site, there's actually a net increase in the emissions first in terms of the baseline. So there's an increase of about 15, 16%, just accounting for sort of the real stuff that was poured on site. And then when you layer in the reductions from EcoPact, we saw that sort of 17% average 17% drop in the overall sort of embodied carbon there. However, so that netting out from our design LCA, there's only about a 5% reduction. But obviously, if we didn't do it at all, we'd sort of be up 15%. So overall, the net reduction is significant. But what we decided is we needed to really also tackle what is contributing to this 15.7% almost first and say, how can we get our actual design to be, actual construction to be tighter to design. And then if you're able to layer in the EcoPact, then you'll see real benefits in terms of being able to reduce on the ground. Oh, sorry. One other thing to note is in this baseline, both baseline numbers here, the design LCA and the as-built LCA, we actually did not include any multipliers for additives in that. So I know you can add sort of a standard multiplier to simulate what weather mix or high earlies and things would do on top of your baseline, but this does not include that. However, the EcoPact data does include weather mix and other additive impact in there. So in reality, if you wanted to include that in your sort of baseline number, your baseline could be inflated slightly and then you could show a higher reduction, but we tend to just be conservative on that. And that's something else we're looking to work towards and standardize in the future. It's like, how do you quantify your baseline LCA and is everyone doing it the same way? I'll get to that again later, but just a side note. Okay, so again, digging into that 15% overage just in terms of our base as-built before EcoPact. So what we wanted to look into is how do we actually break down the strength and volume increases and really where is it coming from, what's driving that. So what we found was that below grade, so this is two charts showing kind of our baseline concrete volume, a little bit of an increase for just like a standard 5% increase to waste assumption. And then how do we actually fare compared to that? So below grade, we actually saw a 2.5% increase in volume on top of the 5% waste assumption. But then above grade, we saw a 6.5% increase on top of the 5% waste assumption, which is actually a very large amount of waste. It's more than doubling our baseline assumption for waste above grade. And that was really strange because we expected actually more waste below grade because you don't form your footings or your pile caps, you kind of just throwing concrete into a hole, and shotcrete is super messy. So you'd think below grade, you'd actually see more waste than above grade. So we're like, that's weird. Let's look into that a little bit further. And so again, this is another way we can slice and dice the data. This shows now, again, level. But then if it's red to the right, that's an overage on our budget assumption. And if it's green to the left, that's actually an underage on the budget assumption. So what you can see here, sort of the lower floors, there is some waste, but really the vast majority of the waste actually occurs, call it in the podium levels, those lower levels, not just like the typical straight tower. Whereas in this typical tower, you actually see we're significantly under on waste. So that's super efficient forming. It's really, once they get in the rhythm with just a plain tower plate, they can just go up and you don't see a lot of waste there compared to in a podium. So what that actually looks like in terms of the massing, just for context, this is what the building looks like. So this structural rendering, really, you can see here's the typical tower that we keep talking about to the left, but it's really almost 2 or 3 buildings, depending on how you slice it. There's this sort of massy stepped podium to the right, as well as some mezzanine levels, lots of transfers, lots of drops, lots of beams and things like that going on. But then once you get above a certain level, it's super clean and easy to construct. And so this massing, especially in those levels, really led to some difficulties in execution on site. And they're just not as clean when it comes to the formworking and things like that, which led to the overages on the waste. And I'll just give Adam a second. I know he has a little bit more of the origin story around some of this massing and just sort of like how this sort of contributes to some of our overall corporate objectives as well.
Yeah, sorry, you're on a roll. Didn't want to interrupt you. Yeah, so I mean, this is kind of an aside, but I think what we take away from this is really just how some of the broader, I guess, economic trends in the industry really drive design, and then by as a byproduct of that, drive carbon. And so, this project was probably purchased the land 10 years ago, probably designed 5 or 6 years ago with the zoning around the same time. And at that time, the market is super hot, land prices are super high. And generally, to make a return, you got to maximize the density on your site and cram in gross floor area essentially anywhere you can. And so that's what leads to designs like this with big, massive, chunky podiums. You see all sorts of stepping and terracing, again, trying to comply with urban design requirements. And you're resulting with a form like this. And this ultimately is a byproduct of the regulatory and financial environment of the time. Today, we would never design and build this building. Today, we've got density that we can't use on sites because the market can't absorb it. So if we were redesigning this building today, you'd probably keep the tower and lose everything else. Um, and so I think it's just as we continue to navigate through this changed market, I think we're seeing a lot more cost discipline on our side, just given that the never-ending price growth has in fact ended, and now it's the cost side of the equation that we really need to control. So hopefully that's just a little bit of context and instruction to people to how all of these different factors kind of come together when developing a project, just in terms of massing design, but then ultimately trickling down to construction efficiency and then at the end of the day, carbon emissions.
Right. Thanks, Adam. So yeah, really that is a lot of sort of the content related to the volumes. And I think we really want to dive into, again, how can we get more efficient, use the materials more efficiently from both the cost and carbon perspective. But then it's also the question of what are the strengths we're specifying and how does that also contribute to cost and carbon. So just an aside, I guess, as Mark kind of touched on at the beginning of the presentation, concrete is specified sort of in terms of its 28-day strength. So when I say it's a 35 MPa concrete, that is specifying the 28-day strength. However, on site, it's not that they don't care about the 28-day strength, but when you're sort of doing forming and formworking and you need to sort of put the form up, pour the concrete, and then a couple of days later you take the form off, really within 3 days is when you need to hit what they call 70% of that specified strength. And that indicates when you can actually take the form off and move it to the next element. So what some people do is they order what's called a high early. So you add high early additive into your concrete, and that makes your concrete cure faster so that you hit that 70% strength within the 3 days. So you can, again, do your cycle time for your form working. However, we don't really do that. What we do instead is sort of similar result, but just a different way around it, is you can actually just increase the specified strength of your concrete. So if the design calls for 35 MPa strength, you can actually just order 40 MPa concrete. And then in theory, you'll actually get 70% of 35 faster because you're ordering a higher strength concrete, if that makes sense. So pretty much that's what's done here. So what that does is it effectively creates a phase shift in terms of your concrete strength distribution that you actually see on site compared to your design. And that's what we're showing here. So you can see the yellow is sort of the initial budget compared to the blue, which is the final design. Again, there's always some tweaking at the end for like column spacing or whatever, which leads to some different differences just between kind of an issue for tender versus issue for construction, call it. But then what you see actually on site is a significant change from that. So you can see pretty much a lot of 25 MPa concrete would have been ordered at 30, 30 would have been ordered at 35, and a lot of the 35 would have been either ordered at 40 or 45 MPa concrete, which is a significant increase overall, and leads to a change in the average weighted strength from 30.91 to about 33. So that's about a 7.5% increase in the average strength. And so what that kind of computes to in terms of cost and carbon, just again, these are super base cost numbers, super schematic. Don't hold anyone to these prices because they're obviously way too low. But really what happens when you sort of have that shift, so we're increasing the average strength by about 2.3% MPAs. And so if you say it's about $3.30 per MPA, overall across that much concrete volume, we'd expect an increase of about 250K in terms of concrete cost. And if you do the same in terms of carbon, that's about 5 kilograms of CO2 per MPa per meter cubed. So that would be about 389 tons of carbon CO2 equivalents on this site as well. So that's a lot of the source of that. Just in addition to higher volumes, if you're also specifying higher strengths, it's really sort of like a double whammy in terms of your cost and carbon impact for every meter cubed of concrete on that site. All right, so cool. So what? We try to always tie some of this like super academic stuff back into what are we actually going to do about it, and how can we sort of work together as an industry, sustainability sort of experts in implementing this stuff. So in short, number one, of course, there's lots of areas to expand the deployment of lower carbon concrete. Of course, we talked about, okay, let's get tighter site coordination so we can hit some of those transfers, get buy-in on weather mix, cold weather conditions, all that jazz. That'll do tons in terms of just being able to, okay, whatever you are ordering, it should be low carbon. That's great. But really, I guess number two is how are we also quantifying that and really reporting that? So if we can improve the accuracy of our design LCAs, so again, like I mentioned before, what is the baseline? Does the baseline include waste? Does the baseline include rate riders for weather mix and other additives? Like how are we doing this, and how can we actually compare to each other in an accurate way? And is there actually more ways that we can be refined in terms of quantifying that waste? It's like, should we be saying, okay, a podium has an average of 10% waste and a tower actually has less than 2% waste? Like, can we actually start to refine both our budgets and our carbon estimates based on real data to support those types of assumptions? And is everyone doing the same thing? And importantly, also is the idea of creating this feedback loop between design optimization and field conditions. So like I mentioned, when we increase the amount of concrete when we increase the concrete strength, how are we actually accounting for that? And so really, it sounds really simple, but I mean, ideally, we would just design what we're actually going to build. And then on the other side, we're actually just going to build what we design. And so you can say, if only life were so simple. But we do have this example, really, like we could even keep it more simple than that. So it's like we know there are some established rules of thumb for increasing strengths, especially in the typical tower. Very simple, just it's a tower. And we know the cycle time. We know what we're going to have to do in order to meet that cycle time. And so in addition to saying, okay, so for slabs, let's say they go from 25 to 30 as just a rule of thumb. And for columns, they go from 35 to 40 as a rule of thumb. Well, can we actually give that information back to the structural engineer and say, okay, these are actually going to get poured higher. So what can we do in terms of optimizing the actual structure to bring the design down? And then on top of that, even those concrete strengths, even though they're at 28-day strength, for saying it's at 35 MPa, sorry, at 28 days, it has to be at least this amount. In reality, when they actually get to 56 days, they're even higher than that. So when we're adding these safety factors on top of safety factors, it just leads to way over designing. And how can we actually feed back between our structural engineer, our concrete suppliers, and our site teams to say, okay, this is what's actually going to get built, and how can you sort of bring down, sort of almost create two models, like this is what's actually going to get done on site, and this is sort of what the minimums are in terms of code, and be able to sort of say, like, there are going to be differences, but how can we actually optimize for what's really going to be built rather than just the theoretical side, which is the challenge. And this kind of comes back to the fourth point of like, how can we use data to really support this? And what I'm calling sort of this buzzword, whatever, portfolio and project co-optimization. So how can we, again, get data for live projects and historical projects and really use them to optimize based on each other? And so here's an example of that. We had worked with our estimating team to sort of start obtaining some metrics for what should anticipated concrete volumes be based on, let's say, underground floor area, which is kind of shown on this line here. And then what happens when a project is a significant outlier project like the one shown? Can we actually flag that earlier? On this project, we actually did do an LCA at the end of design, but since we actually didn't have good metrics to compare to, the overall embodied carbon impact or intensity for this project was actually in spec. So we didn't ask any questions. It's like, okay, we met our target, looks good. But when we start diving into the actual efficiency of the structure, it's a huge outlier. And sort of the amount of structural inefficiency that was in this project, if we were able to just bring this one down into line with the rest of them, these are the anticipated savings of about 3.5 million in terms of concrete and rebar that could have been avoided, in addition to probably hundreds of tons of carbon emissions as well. So really being able to use data to identify outliers is sort of the first step to make sure this type of thing doesn't ever happen again. But we just don't want to establish the system so we can flag these things and catch them right away. And then that sort of feeds into the next thing as well of just how can we actually then start to build out our data set and really move things, not just in line with outliers, but move the whole trend line down. And how can we start to do that by working more closely and collaborating across different disciplines. So this is another example. So again, like what we've learned is that different structural engineers will have a different style. So even outside of just building constraints or building design, like there are certain engineers who will specify lower volumes but higher strengths, something like B, or there's other engineers that specify higher volumes but lower strengths. And we want to be able to start to capture that and say what is actually the best sort of solution for optimizing for carbon cost and schedule too. Like once you're able to maybe pour, like there's going to be always trade-offs between, okay, so it's higher strength, but so it costs more, but can we actually use less of it? And maybe the benefits in terms of schedule are outweigh the kind of additional costs and carbon impacts for the change in design. So anyways, we just want to be able to start collecting this data, sharing it with others as well, and sort of comparing notes and saying, like, are there certain metrics that we can start using across the industry to say, okay, this is the sign, like this is the benchmark for an efficiently designed building versus an inefficiently designed building. And like, can we start establishing those and having these rules of thumbs, just to be able to flag stuff early in design, as well as feeding that into our LCA processes as well. So that's it. Thanks, everyone. And I think we'll open up for questions.
And there's a whole bunch in the chat as well, so maybe we start with those.
Yeah, thank you so much. That was great. Both presentations were really informative, and we have quite a few questions here. I'll start from the first one. So I think this one's for Mark. Do you provide support to engineers regarding the extended maximum strength time for your products? I usually find resistance from structural engineers to change that, as well as an excuse for scheduling.
Yes, that's a great question. So when we brought this out to the market, there was definitely a bit of a shockwave, especially for engineers on the curing delays, specifically for our EcoPact Prime. We've learned it's crucial before the job even begins to be transparent on those potential delays for some of those mixes, and our team does work hand in hand with the engineers to adjust the mix designs and the GWPs depending on which elements require different curing times. So, yeah, with proper planning before the project begins, we can kind of work with the engineers again before the project even begins to properly plan on which mixes can use lower carbon, which elements, sorry, can use lower carbon concrete mixes versus some that can't. So, yeah, takes some planning, but you can definitely hit your GWP targets with scheduling, with some proper planning beforehand.
Great. I think another one for you, Mark. It's broken into two. So what's the cost premium for EcoPact mix? And I'm guessing it changes maybe between the Prime and the standard. And then the second one is for LEED V4. They run into roadblocks with suppliers for reporting the recycled content, since it's proprietary. So does Innoconn support that for LEED?
Yep. So for the first question, the cost premium for EcoPact is not too crazy. It all depends on what the cost of slag and fly ash currently is. Right now, there's not a shortage, but with the steel manufacturing being down, the cost for slag has increased. So therefore, the EcoPact costs increase as well, but it's nothing major for now. That can change. With the LEED version 4 projects, I can't speak on all suppliers, but for Innoconn, we're happy to supply all the information regarding recycled content. We've done dozens of LEED projects in the GTA alone, and we've never had issues supplying that information. So as long as you're using EcoPact and we know it's a LEED project ahead of time, then we're happy to supply that information.
Perfect. Okay, and just one more for you, Mark. So Alistair says that he's really excited that this is becoming more readily available, that you've described your recipe requiring byproducts from steel and coal, and credits for using the byproducts. But as you cease to push coal production entirely, to cease coal production entirely and decarbonize steel, how will this affect the makeup of your product? How do you account for the A1 to A3 of these ingredient materials in your EPD?
Yeah, so that's a great question as well. And yep, for both coal and steel, eventually the goal is to cease production entirely. So that will be it could potentially be an issue for EcoPact further down the line, but there are a lot of innovations that Amrise and both Innicon, even here in Toronto, we have the lab, and there's a lot of innovations being done right now with carbon injection, um, different types of admixtures as well. So hopefully by the time that those products, if they do eventually cease to be made, there's other innovations that are already in the works to keep the low carbon concrete going. And with the A1 to A3, that is basically accounted for. So we account for all of the emissions from the manufacturing of our byproducts, so cement and aggregates, uh, right up to loading the concrete at the plant, and as soon as it leaves our gate. So all the transportation emissions are included for all the raw material and the concrete up to the point where it leaves our ready mix facility front gate. The only reason we don't include the transportation emission of the concrete truck to the job site is because it's very hard to track that. And you can be sitting in traffic longer some days than others. So it basically includes the transportation emissions right up to the point where it's loaded and it leaves the gate at our yards.
Great. Okay, so I think the rest of these questions are for Daniels. A few came up concerning EcoPact with Weather Mix and specifically comparing it to a traditional concrete with Weather Mix. And then also concerning the EcoPact with Weather Mix, like how is its workability and cure time comparable to a standard? If Daniels wants to take a stab at that.
Yeah, so as I mentioned, we did some detailed break testing. So we took, like, normally you would only take, call it a handful of break tests in terms of the cure time. And the Weather Mix and the EcoPact were identical, pretty much. Sorry, the Weather Mix with EcoPact and traditional were identical in terms of the testing that we did. However, I guess in terms of the workability on site, I think there's sort of mixed feedback in terms of that. I think that's Trish actually mentioned that the concrete with Weather Mix is hard to work with as it sets up extremely quickly. I think that there were some challenges in terms of the EcoPact being slightly harder to work with, and then with the Weather Mix it does set up faster. But I don't think that was a significant driver. I think overall we got positive results in terms of the workability on site. Again, I felt more like the perceived schedule risk of using something that was unknown, calling it a pilot, led to more of it being sort of pulled during those times rather than actual data. And I totally get that. I mean, when you're being pushed every day to hit your schedule targets, and then you're also being layered on with this sort of like innovative pilot, I think during the hardest conditions, including the weather mix times, it's just kind of, I don't want to say it's the first thing to go, but it's easy to, it's not easy, but it can be something that can be sort of like pulled to mitigate risk, even if it's only a perceived risk, which I think I've said a few times, but it is kind of difficult to execute.
Yeah, definitely. So one other question here from Alan, or two questions from Alan. So, what baselines were used for the as-built LCA analysis? And then also, just has Daniels explored setting a carbon reduction limit on their projects moving forward? So, for example, a 10% reduction using carbon budgeting for the whole project?
Yeah, so the baseline, I guess, EPDs were the CRMCA Ontario ones, just like the baselines that were sort of identified through their industry EPD. And again, for the baseline, both the baseline design LCA and the baseline as built, there were no multipliers added for additives. So those were just like straight from the EPDs there. In terms of setting carbon reduction limits, I mean, we work closely with Innicon, and we love that the EcoPack product sort of is able to be you're able to get the product specific EPDs for including additives, including exactly the mix codes that were being sent on site. Because there's way more than just strength and volume and weather mix. There's tons of different additives, different slumps. It's crazy. There's like 60 mixes that we'll use in a project. So we get the type 3 EPDs for all of those, which is just a huge value add in terms of the data accuracy. I think going forward, we do want to be able to use this data to say, okay, like we were able to achieve a certain reduction on this project. So can we set that as sort of like the new high water line in terms of minimums going forward? And being able to work closely with like the Innicon team in terms of what is the sort of distribution of their different products that will get us to a certain target. But this was sort of the first step in saying, okay, what can we do rather than just sort of blindly setting a target without knowing what's actually executable was the intention.
Great. And then another question from Sanjana. So how did you report on the as-built volume? Like, how is that included in the contract? So was it something in the project spec from the contractor? Was it like their responsibility? I guess at what point did you tell them that they had to do that?
Yeah, so we're actually a developer and a builder, so we do our own construction management. So it was actually our own site team for every site, not just this one. There's actually a concrete log, which sort of tracks every truck coming in, what's being poured, when's it being poured, what's the mix on every job. So this was we pretty much just added a couple columns into that existing log saying, hey, can you also tell us workability, indicate well, in the mix code, it actually already told us if it was EcoPact or not. And we were able just to use that log, which has super detailed information in order to produce all this data. So I'm not sure if other construction managers do the same, but it's honestly, I think it comes from more of an accounting origin, to be honest, to be able to say, hey, this is actually the concrete that we should be paying for. Does it sort of match what we're being invoiced for? And then again, this is sort of the link between marrying cost and carbon. It's like if you're paying for it, then there's sort of the trail that you can follow in terms of carbon as well. So we're kind of pulling on those strings to be able to get the data.
Perfect. And one last question from the chat. What's the approximate carbon burden that's attributed to the use of blast furnace slag and EcoPact? This one's probably for Mark.
Yeah, sorry, Mike, I don't have the exact numerical value for that one. It is a byproduct though, right? So it's being used back in the construction process instead of going to a waste facility. But yeah, unfortunately, I don't have the exact kilogram numerical value.
That's okay. You have another question. Has the concrete mix made any headway in the waste water sewage treatment facilities?
Yep. We have made I believe we've had some EcoPack mixes in the water treatment facilities. It does get a little tricky because of the waterproofing admixtures like Kim and Zypex that are also typically used in those treatment facilities. But we can definitely design and create EcoPack mixes as part of the S classifications for water and sewage treatment facilities.
Great. And then just one question that I had actually for Daniels. And you did the comparison on just the structural part of the building. Were you able to extrapolate what that would be for the whole building if you include the envelope? I think it was 17% savings if you don't account for the as-built. So what would it look like if a project maximized on EcoPact for both envelope and structural? Like what would that percentage reduction be?
Envelope, oh, like the full like ECI reduction?
Yeah, exactly.
That one's tricky because I mean we're looking to create projections for design LCAs of how much we can assume that we can use, I guess, in terms of the design, if that makes sense. So it's like, let's say you had a design LCA and it's like, I'd love to be able to say, it's like, okay, that 17% reduction that we saw, just drop your structure by 17%. That would be like an ECI reduction of, let's say, like 10 or something, 15. But I feel like it's not that simple because we're getting a little bit caught up in terms of renormalizing our baseline to now be more accurate in terms of like the waste and the strength changes. So it's not quite as simple. Like we don't want to take the benefit of something that sort of happens at a site level without also kind of taking, call it the the negatives, if you know what I mean, in terms of like, we don't want to just see the benefit without kind of renormalizing to a higher baseline point in the as-built. So we haven't quite figured out how it's going to distill down into adjustments to our design LCAs. Sorry, that was a bit of a cop out, but we're still working on it.
No worries. No, that makes a lot of sense. It's definitely complicated to account for everything. Okay, any last questions? I think we have 6 minutes left, but if nothing, then I think we can end the webinar here. And thank you everybody for joining. I think we'll likely have another webinar from CLF in the next month. And feel free to revisit this webinar. We'll be posting it onto our website and through our LinkedIn. So thank you so much.
Thanks, everyone.
Thanks, everyone.
Have a great day. Bye.
Bye.